Okay, good evening. Welcome to Math for Kids number 66. Okay, today we're going to look at the equation x squared minus 31y squared equals 1. Whoa. And that's going to involve us computing the continued fraction for the square root of 31. Now, if you go back to Math for Kids 63, that's where we started this little excursion. And on Math for Kids 64, we computed the continued fraction for the square root of 2 and saw a bunch of cases where x squared minus 2y squared was equal to 1. On Math for Kids 65, we looked at x squared minus 3y squared equals 1, or in other words, the continued fraction for the square root of 3. Today we're going to do kind of a complicated one, but we're not going to do all the arithmetic. We're not going to do the split, flip, and wrap, although we could. It's just that the continued fraction for the square root of 31 is a little crazy. So, first of all, can we say anything about the square root of 31 before we start? What number is just a little bit less than the square root of 31?
I don't know.
Well, what's 5 squared?
It's 25.
Okay, so 5 squared is 25.
It's between 5 squared and 6 squared.
6 squared is 36. So the square root of 31, which is between 31 is between 5 squared and 6 squared. So the square root of 31 is a little bit bigger than 5. Or in other words, 5 is less than the square root of 31. And the square root of 31 is also less than 6. Okay?
Yeah.
So that means we're going to start out with 5 plus something. And in fact, the continued fraction for the square root of 31, which I've written up here, it looks like this. 5 plus 1 over 1 plus 1 over 1 plus 1 over 3 plus 1 over 5 plus 1 over 3 plus 1 over 1 plus 1 over 1 plus 1 over 10 plus 1 over 1. But you see it repeats. It goes 1, 1, 1, 1, 3, 5, 3, 1, 1, 10. 1, 1, 3, 5, 3, 1, 1, 10. And it goes on forever.
To infinity.
To infinity. Maybe beyond. Okay, so let's compute the convergence and see what we get. Now, 5 times, oops, I made a little mistake writing our continued fraction machine down, didn't I? 0, 1, 1, 0. 5 times 1 plus 0 is?
Is 5.
5. 5 times 0 plus 1 is?
1.
1. 1 times 5 plus 1 is?
6.
6. 1 times 1 plus 0 is?
Is 1.
1 times 6 plus 1 is?
1 times 6 plus 5.
Plus 5, sorry.
11.
Is 11. 1 times 1 plus 1 is?
2.
2. You want to write?
Yeah.
Okay. 3 times 11 is?
33.
Plus 6 is?
39.
39. 3 times 2
6.
plus 1 is?
7.
7. Okay, good. 5 times 39, now luckily I've written some of these down ahead of time. 5 times 39 plus 11 is 206. 5 times 7, you know.
35 plus 2 is 37.
37. The next one becomes 657 over 118. The next one becomes 863
Well, this is only
over
not even half.
155. Well, no, it keeps going on for infinity. And this last one we're going to take a look at is 1,520 over 273. Whoa. Okay. So, this is crazy. If this works like we saw with the square root of 2 and square root of 3, these fractions, 5 over 1, 6 over 1, 11 over 2, 39 over 7, 206 over 37, should all be really, really close to the square root of 31. Okay? So if 5 over 1 is approximately equal to the square root of 31, that means 5 squared over 1 squared should be approximately 31. Okay?
Yep.
Well, let's check.
What's 25?
Well, 25 is kind of close to 31. It's not that good of an approximation.
Yeah, not good of an approximation.
6 over 1 would just be 36, which is also kind of close to 31, but it's not that good. Let's look at 11 halves. Is this approximately equal to the square root of 31? Okay.
This,
well,
is this approximately equal? Is that
11 squared? You know what that is, right?
So it's 121.
Is 121 over 4 approximately equal to 31? Well, does 121 approximately equal to 4 times 31? Remember, we can multiply both sides.
It's 124. No, well,
Right.
Yeah, 124.
Okay. It's actually pretty close. Okay. So this, which is, by the way, 30 plus 1/4, is indeed approximately equal to 31. Okay.
Yep.
And here we have 11 squared minus 31 times 2 squared. 11 squared minus 31 times 2 squared, which is 121 minus 124, is minus 3. Shoot, we were hoping to find something equal to 1. But it's close, right?
Yeah, only off by 4.
Let's try 39 over 7. Let's see what we get. Is 39 over 7 approximately equal to the square root of 31? Well, 39 squared is 1,521. What's 7 squared?
49.
Does 1,521 over 49 approximately equal 31? Well, it's hard to say. But I did check what this means. 1,529 would be approximately equal to 49 times 31. Remember, I can multiply both sides of the fraction by 49.
Yeah.
Yeah. And 49 times 31 is 1,519.
That's close.
That is close. In fact, 39 squared, which is 1,521, minus 31 times 7 squared, which is what I have here, 31 times 49, equals 1521 minus 1519, which is
Just 2.
2. It's really close. Whoa! But it's still not solving our equation. In fact, in order to solve our equation, we're going to have to look at this one. 1,520 over 273. Does this approximately equal the square root of 31? I don't know. I don't know what 1,520 squared is, do you?
Do you have it down?
I did. Luckily I wrote it down.
You.
It's 2,310,400.
Wow.
Over, this is when I square this, 273 squared. You know what, I didn't write down what 273 squared is, but the question is, does this approximately equal 31? And I did write down 31 times 273 squared. So the question is, does 2,310,400 approximately equal 31 times 273 squared? Well, 31 times 273 squared is 2,310,399.
And that satisfies our equation.
It does satisfy our equation because 1,000, write this down for me, will you? Will you write down 1,520 squared minus 31, minus 31 times 273 squared equals 1. So here's the neat thing about continued fractions for square roots. Okay? If you have an equation like this, x squared minus some number squared times y squared equals 1, you get the continued fraction for whatever the number was here. And you look to where it starts repeating. Okay? Now, the continued fractions for these square roots, it turns out, for square roots of integers, always repeat. And they always have the form that we have here, where the first number is half of the number where it starts repeating. Okay? You see the pattern where the 10 starts showing up?
Yeah.
And this 5 was half of the 10?
Yeah.
So, for most numbers, you go out to where just before it starts repeating, just before where the number is double, so 5 goes to 10, and that's going to solve your equation. But sometimes it doesn't solve the equation, and we're going to give an example of that tomorrow.
Okay.
Sometimes it's, instead of being equal to 1, it's equal to minus 1.
Cool.
Cool. And then to get the one where it's equal to 1, you have to go all the way out to the next one. So can you imagine how large a number we would have if we went all the way out to where the next 10 was?
You'd better calculate that on your
Yeah, we'd have to use Mathematica to calculate that. But this is really an amazing thing about continued fractions. And I picked 31 because the continued fraction for 31 is really complicated. But you you can solve this equation by writing down the continued fraction, writing down the convergence, so the fractions that are almost equal, and eventually you come across a solution. That's really neat, isn't it?
Yeah.
Because how can you imagine trying to solve this equation some other way?
Well,
I don't know how you do it, actually. But I think this is a really neat way.
it's a good way.
Yeah. All right. Good job tonight, honey.